Hello and welcome to our third discussion on random variables. We're going to talk about binomial and geometric random variables. Quite a long section, a lot to cover. Class is going to take two class sections, a lot of very interesting information, some fun calculations. So let's get started. All right, so we're going to talk about binomial settings and binomial random variables, binomial probabilities, mean and standard deviation of binomial distribution, binomial distributions in statistical sampling, and then we'll end with geometric random variables. Really, this should be two sections, one on binomial, maybe three, one on binomial probabilities, binomial distributions, and then geometric random variables. All right, so binomial setting. All right, what's the first word that comes to mind when you think of, or idea that comes to mind when you think of binomial? Bi means two. Nomial, name, two names, or so two possible outcomes. So binomial setting, when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. There are four conditions. One, binary. So a lot of the binomial work we're going to use around, and you can use around computers and programming. Outcomes are considered success or failure. So that's the first requirement. Second, independent. Trials must be independent. So each trial cannot affect the outcome of the next. The number of trials, N of the process must be fixed in advance. And four, the probability of success is constant for each trial. All right, so BINS. And when you answer a question, an FRQ or an AP Stats FRQ, you want to remember BINS in order to qualify for a binomial setting. Binary, independent, number, success. Success and failure, independent trials, number is fixed, and the probability is constant. All right, so BINS. All right, so here are some examples. I toss a coin 5 times, and I count the number of heads. I know N is 5, probability is the same, 0.5 for each. Spin a roulette wheel 8 times, record how many times the ball lands in the red slot. I don't know what the probability is. I think it's 50-50. 8 is the number of trials. Take a random sample of 100 babies born in the U.S. Count the number of females. All right, so females born, I believe, is slightly higher than 0.5. So these all qualify. So either get a male or a female. These all qualify as binomial random variables, or a binomial setting. Okay. All right. So binary, independent, number of trials fixed, probability of success is constant. All right. The count, so binomial random variable, count of X successes in a binomial setting. So example, the number of times you flip a head, if you flip a coin 5 times, binomial distribution, the probability of distribution of X with the parameters A, N number of trials, and P, the probability of success for X. So when we fill out the values then, it's N is equal to 5, P is 0.5, and then X is the number of successes that we get from the 5 flips. All right, and we can get, if I flip a coin 5 times, I get 5 tails or 0 heads, 1 head, 2 head, 3 head, 4 heads, or 5 heads. Those are the options. All right, so we're going to figure out the probability of each set occurring 0, 1, 2, 3, 4, 5. And so this is how we're going to do it. So probability that X is equal to 0 is the probability that the number of heads is 0 if you flip a coin 5 times. X is equal to 1. Out of those 5 flips, you flip 1. Ooh, I'm missing a 2 here, 3, 4, and 5. All right, so this is how you would set it up. I think I did this for space. All right, so I set this up. And then we would run the binomial distribution and do the calculations, and we're going to do that in just a moment. So determine whether the random variables below have a binomial distribution. If so, define N and P. The probability that a child has type O blood is 0.2. You randomly select 5 children. Let X equal the number of children with type O blood. Number 2, shuffle a deck of cards. Pick 10 cards, one at a time. Without replacing the card, let Y equal the number of aces you observe. 3, shuffle the deck, pick 10 cards, replace the card after picking. Let W equal the number of aces you observe. So think about this. Do each of these satisfy the bin's requirement? And I'm going to show you the answer. All right. So the first is, yes, the probability that a child has type O blood is 0.2. Randomly select 5 children. Let X equal the number of children with type O blood. Okay, great. So binomial independent. The number of trials is 5. Probability of success is 0.2. So we met our bin's requirement. Number 2, shuffle a deck of cards. Pick 10 one at a time without replacing the card. Let Y equal the number of aces you observe. Binomial dependent, so it doesn't qualify, because when we don't replace a card, we have fewer cards left, so the probability of picking another card goes up. That's not picked. And then third, shuffle deck, look at the card, replace the card after picking, keep picking until you get an ace. Let W equal the number of aces you observe. We don't have a fixed count. We do have a probability. It is independent. It is binomial. But because we don't have a fixed count, we cannot evaluate this as a binomial problem, the binomial random variable. Okay, so this brings us to our first homework problem, 6.3.1. Determine whether the random variable below has have a binomial distribution. If so, define N and P. You can just list BINS and then state whether or not they meet all the 4 criteria. That would be good work for you to do. All right, you can pause here. I'm going to move on. All right, so next we're going to talk about binomial probabilities. So binomial distribution experiment. So example, 90% of teenagers have cell phones. If you randomly select 10 teenagers, what is the probability that exactly 7 of them have a cell phone? So binary, yes, cell phone or not. Independent, yes, one teenager having a cell phone does not affect whether another teenager has a cell phone. Yes, number, you pick 10. Success is exactly 7 of those have a cell phone, and we have a probability, and that's 90%. Okay. So the way that we're going to do this, first I need to talk about combinations real quickly with you. So combination is the number of outcomes given some parameters based on the number of possible outcomes, the number of selections, and whether or not order matters. So we're not going to go into deeply what combinations are. Hopefully you cover this briefly in Algebra 2, or maybe even briefly in Calculus BC. So N equals the number of trials and K equals the number of successes. And we have a combination, and that formula is N factorial divided by N minus K factorial times K factorial. All right, and there is a, you can go to your TI 84, and there is a combinations button, which we'll have to go through in class. And you're going to type in combinations, and you're going to choose possible outcomes and then the number of specified outcomes, where in this case combinations order does not matter. All right, so we're going to use that formula, and we're going to put that into our formula for binomial probability. That is, the probability of K successes is equal to N number of trials, combination K number of successes, times, so this is combination value, times the probability of success to the power of K, times 1 minus, so the complement of P, to the power of N minus K. All right, so let's put this into context, and let's work out a problem. Let's see how this works. All right, so I have 90% of teenagers, so that's the success, right, have cell phones. I pick 10, and I want 7 of them to have a cell phone. The probability of X is equal to 7 is 10 factorial over, so N factorial divided by the number of 3 factorial times 7 factorial. So going back to our equation for combinations. So n is the number of trials minus k. So I have n factorial, which is the number of trials 10, over n minus k factorial, the number of successes is 7. 10 minus 7 is 3 factorial times the number of successes 7 factorial. Right, so we're using this combination formula to find this value. So 10 factorial, number of trials, and then 10 minus 7 is 3 times the number of successes factorial, 3 factorial. And so we get, and by the way, factorial means 10 factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm assuming that you know this going into this lesson. We might have to pause here for a moment to evaluate what factorial means. All right, so 10 factorial, or any n factorial, is n times n minus 1 times n minus 2, etc., until we get to n factorial is equal to n times n minus 1 times n minus 2 until we get to 1. All right, times 1. All right, so you have to evaluate that. So again, I'm assuming that you know this already. And so we're going to evaluate, we're here, sorry. So 10 factorial over 3 factorial times 7 factorial on the combinations is going to be 120 times 0.9 to the power of 7 is 0.478 times 1 minus 0.9 to the power of 3 is 0.001. So I end up with 0.05736. This is the probability that there are exactly 7 teenagers that will have cell phones if you randomly select 10, where in the entire population, 90% of the teenagers have cell phones. All right. So this is our look at the factorial value. So going back through this here, I have a combination of n, choose k, p to the power of k, 1 minus p complement of p to the power of n minus k. So that's how I got those values. So probability of 7 successes is equal to combination of 10, choose 7. Probability of success to the power of 7 times 1 minus the probability to the power of 3. All right, so this is how I'm evaluating these. So binomial distribution is a probability distribution in which there are only 2 possible outcomes, with n trials, flipping the coin, n times, where we have k successes. All right, so let's take another example. You flip a coin 5 times. What is the probability that you flip 0 through 5 tails? Probability of flipping a tail is 0.5. So we're going to go through this for all of them. So we're going to calculate each k value, 0 tails. I have 5n 0 successes. 0.5 to the 0 successes. 1 minus the probability, the complement, to the power of n minus the number of successes, 5. Right? And then I end up, if I go through all the calculations here, getting the probability of 0 tails, 1 tail, 2 tails, 3 tails, 4 tails, 5 tails. And the sum of all these should be equal to 1.00. In fact, I believe it is or is very close. All right, so this is an evaluation, binomial distribution for all the probabilities. Remember, I have one more because I have the possibility of not flipping any, 0 through 5. All right, you can look at the work and pause here. I'm going to move on. All right, so there's also a binomial, PDF and CDF, which you're going to use to calculate exactly 7. You're going to use a binomial PDF. And then you're going to have 10, which is the number of trials, the probability of success, and then the number of successes exactly. To calculate less than, you're going to use the CDF, binomial CDF. And to calculate greater than, you're going to use binomial CDF, 1 minus binomial CDF. All right, where binomial PDF and CDF have the number of trials, probability of success, exactly the number of successes for PDF, and then less than or equal to the number of successes for CDF. All right, so this is going to bring us to your homework problem 6.3.1. You flip a coin 4 times. What's the probability that you flip? 0, 1, 2, 3, 4 tails. Probability of success is 0.5. Right, so you're going to define NP and K, and then you're going to do the work, and then you're going to come back for the next part of this lesson. So please make sure you pause this and copy this down or take a picture. I'm going to stop.